Hello again, everyone, and welcome back to the SEM part of our course today. And in this part of the lecture, we will talk about the model comparison in the structural equation modeling. First, let's recap what we already know about the goodness of fit in the covariance-based SEM. So when we fit our model to the data, what we basically do, we assess whether our model implied covariance matrix reproduce the observed covariance matrix. And when we fit our hypothesized model, we basically ask two questions. And the first question is if we ignoring any important links in the model. And if we ignore such links, this would mean that we ignore important processes in our study system. Also, if we are missing important links, then our parameter estimates may be not correct, and also our model would be not specified correctly. So, when we fit our model to the data, we also ask the question whether the model represents the data well, but this in the SEM also is equal to the question whether we missing important information in our model. And the second question is if all the included links are supported by the data. And we will test both of that questions in Lavaan today. But before we dive into this test, it is important to understand that the model selection procedure in the SEM is not strictly based on the statistical inference, but it is also based on the beliefs of the researcher, on the knowledge of the researcher about the study system. So SEM is not a null hypothesis testing, but it's also a way to evaluate our theory with which we started. So we started with the theoretical knowledge from literature or from assumptions or from logical arguments or from previous data. And based on that, we built our hypothesized model. And that's why when we decide which links we have to include in a model, we should base this decision not only on the statistical evidence, but also on our a priori knowledge about the study system. And now let's address our first question on whether we ignoring any important links in the model. For this, we will again use the data of Grace and Kelly, which you used for your task today. But we will use not identical models that you used for a task, but a bit different, which misses the link from distance to richness. And here is again our model, and I specified it in Lavaan. And use data Kelly, with which I feed the model. And here is the summary, and I need the standardized coefficients here. And the output here in blue, it shows us that the chi-square of 17 with 2 degrees of freedom and a p-value less than 1 in 1000 indicates a large difference between data and model implied covariance. This means that our model fit is poor, and this leads us to the question, what should we have included in this model? Which links are missing here? And to see these missing links, we need to know the differences between the observed and the model implied covariance matrices. And as you might remember, such differences are expressed by the residuals. And to get the residual correlation matrix, we can use function resid to our model. And I use here argument core because I want to see the residual matrix in standardized form. And I use $sign and argument co because residual function produce quite a lot of different information, and I want only this part of table be shown here. And as you can see here, we see a big difference between the observed and the model implied correlation between distance and richness. So we can say here that both the chi-square statistics and the residual matrix shows us that the link from distance to richness should be included in the model. We also can ask Lavan for help in knowing where to look for suggested changes to our model. And Lavan can compute for us the modification indices, which are also called Lagrange multipliers. And these indices, they calculate how much our model fit our chi-square, how much it will improve if we include specific link to our model. And we can request such indices using the argument mod indices equal true in our summary function, or simply to use function modification indices to our fitted model. And here in blue is the output of this function, and you can see here that the Lavan gives us the modification indices ME for each variable in our model, but also for each possible relationship between variables. So as you can see here, double tilde are correlations and single tilde are regression. And MI, this modification indices, show the difference in our chi-square if this specific relationship will be added to the model. And the basic rule of thumb is that we look for indices greater than 3.84. And this value, 384, is a critical value of chi-square with a single degree of freedom for p-value be equal 0.05. You might remember this from the chi-square distribution table. Also, we can ask Lavan to show us only the values of modification indices equal or higher 3.8. For this, we can use the argument minimum value equal 3.8, let's say, in our modification indices function. And then you will get output where your MI values are only equal or higher than 3.8. And again, we have to be very careful with this modification indices to be sure that we are not fishing for a significant data. This is because, as you remember on the beginning of this lecture, I mentioned that the selection of the models or the choice which links are present in a model is a balance between the theoretical knowledge that we have and statistical evidence. So we cannot rely 100% only on the statistical inferences. And also want to mention here that this is not a good practice for the confirmatory model when we want only to confirm our specific hypothesis. However, structural equation modeling can also be used for the exploratory modeling. So in that case, when we search for the links only based on the statistical inferences, then such approach would be fine. And now what we see from this result, that Lavan gives us high modification indices for the correlation between richness and heterogeneity and richness and abiotic conditions. This would mean that instead of having the causal link, here we would have correlations. And this means for our study system that we have some other variables, some other factors here, which affect both of these variables. And knowing our system, we rather decide that we have causal effect and not correlation between these variables. Then when we inspect further our modification indices, we see that there are high indices for the relationship between richness and distance. And this can be or effect of distance on richness or effect of richness on distance. And logically, we can understand that species number of plants on plot cannot cause the distance of plot to coast. So that's why, of course, we decide rather to have the effect of distance on richness and not vice versa. So now we can take this model and check if it changes the fit of our model. So here I fitted the model 2, which includes the additional link from distance to richness, and we fit our model and we want to extract the results. And here are the results. And if you want to compare them to model 1, you will see that our model strongly improved. So our chi-square statistics and the p-value is strongly significant, strongly high, meaning that adding this one link in our model made really big difference. We also can go further and compare our two models using the likelihood ratio test. And you remember that we made this test already yesterday. It's also known as a chi-square difference test. So for this, we just use function ANOVA and we compare to our fitted models here. And the output table here gives us the information for two our models, their degrees of freedom, the hierarchy and the Bayesian information criteria, and chi-squares. And most importantly, that it calculates the chi-square difference between these two models and the degrees of freedom difference and the p-value. And the p-value is strongly significant here. It means that the likelihood ratio test also supports the model 2. And now when we know that we don't have any missing links in our models, we can address our second question, whether the all included links in a model are supported by the data. But in this case, if you want to compare multiple models in order to test different links in a model, the use of chi-square difference test based on a p-value approach is a bad practice. And this is because if we do such multiple tests, then our cutoff for the significance of p-value to be 0.05 is not valid anymore. So we can say that the likelihood ratio test is used when we compare two nested models, simpler model and a more complex model. But when we want to compare multiple models, a good practice is to use the information theoretic approaches like archaic information criteria and Bayesian information criteria. And also, when we use these informatic theoretic approaches, our models are not required to be nested like in likelihood ratio testing. Also with this slide, I would like to remind that when we fit and compare and select our models, we have to remember about the principle of parsimony. And this figure very nicely visually expresses the not necessary complexity when we overfit the models. And the archaic information criteria is parsimony adjusted for model complexity. As you can see, the formula for the AAC calculation includes the number of estimated parameters in a model. Also, the archaic information criteria includes the chi-square, our model fit. But the AAC is an asymptotic property, and this means that it is true when the sample size becomes larger. That's why it makes sense to adjust it for the sample size in small samples. And for this, we can use the AAC lowercase c, which is corrected for the small sample size. And you can see that in the quantification of this index, we have a number of samples included. Also, from this formula, you can see that it has much more complex parsimony correction term in comparison to the AAC here. Also, we can use the Bayesian information criteria, and the formula you can see here, it includes model fit, degrees of freedom, and also corrected for the number of samples. And whether we use the AAC or AAC corrected for sample size or BIC, the guidelines for the simple interpretations are the same as shown here. So if the difference between the values of our information criteria is lower than 2, then we can say that our models are the same. We have substantial equivalency between them. And if the difference range from 4 to 7, then we have weak similarity or weak equivalency between models. And if this difference is larger than 10, then we say that these models are not similar. And now I would like to compare our two models using the archaic information criteria. And the first model is called fully mediated because the effect of distance on richness here is only indirect, mediated by abiotic conditions and plot heterogeneity. And in the second model, it's called partially mediated because in addition to these indirect effects, we have direct effect here. And before we use the archaic information criteria, we have to check the sample size. And we know from our data that we have 90 samples. And in the archaic information criteria, the basic rule of thumb is that if we have less than 250 samples, then we cannot use it. We have to use the information criteria corrected for the sample size. And we can calculate the AAC corrected using the package AAC cmod avg, where we use function AAC tab and we list all our models that we want to compare. Also, we can rename the models. For instance, I call them full and partial based on the type of the mediation. And the results here give the values of AAC corrected for each model. And the delta AAC, it's the difference in the AAC value for each model to the model with the best fit from these two models. And here you can see that this is the model 2 has the best fit. Also, we want to see whether there are other models that are equivalent to our model 2. And for this, you remember from the previous slide, the AAC difference would be lower than 2. And in our case, the difference is much more higher than 2, then we can say that these two models substantially differ among each other. But if our model 1 would have delta AC lower than 2, then we might choose this one because it's more parsimonious and more simple. In addition to the delta AAC, the output table also gives us the k-values, and these are the number of estimated parameters in each model. Also, we can see the AAC weights here, and these are the standardized measures. They are calculated using our delta AAC values, and they give the relative support for each model. These weights range from 0 to 1, and 1 means the highest model weight, and therefore the highest support for the model. Also, there are other things presented here, such as the cumulative weight and the raw log likelihood, but neither of these are important for our discussion today here. And now I would like to show an example how to compare the models if we have the sufficient sample size, which is 250. So for this, we can use the function AAC, where we list our models, and this function gives us the values of AAC for each model in this column 2. And then we can calculate the delta AAC, which is the difference in AAC for each model to the model with the minimum AAC from the set of models which we compare. And here we see this delta AAC calculated. And also we can rank our delta AAC in ascending order. For this I use package dplyr and function arrange. And here you can see the script. And ranking data in the ascending order is very helpful, especially when we have multiple models which we want to compare and if we want immediately to see the best fit. And now it's time for the tasks. And in this part of the lecture, you will have two tasks to do. The first task is dedicated to the model comparison. And in this task, we again will use data Cayley from the package piecewise.em. And you see the model 1 and model 2 are the models that we used during this lecture. And your task is to take these two models and extend them by adding model 3, model 4, and model 5, and to compare them. Please note that in model 5 you have the correlation between abiotic conditions and plot heterogeneity. And your tasks are, first, to think what does it mean to have this correlation in a model 5? What is the scientific meaning behind such a correlation in our system? And second, you have to specify each model in Lavaan, need to feed each model using data, Kaylee, and compare the models using archaic information criteria. And you know that our sample size is less than 250, that's why you have to use the corrected for sample size AIC. And then based on this analysis, you have to select the best model. And the last task for today, task 3, is a test of mediation. And in this task, we will use the project that you already know on the grasslands, which we have used in the first lecture. And here you can see the data, but these are not the same data set. It's data set grassland data 2. So here you have the different hypothetical model, so take care that it's not the same as we used in the first lecture, as well as the data are different. And for each variable in this model, check the assumptions of the covariance-based SEM. So using the first part of the lecture today. And then if there are any violations of these assumptions, use the needed procedures to adjust for these violations. And you can see slide 30 in part 1 of the lecture today for some help. Also, follow the procedures in this specific part of the lecture to test the next two questions. And the first question is, are we ignoring important links in this model on figure 1? And second question is, are all the included links supported by the data? And this was the last lecture for today and the last task for today. You have quite a lot of information to digest. Looking forward to see you during the seminars. Good luck and goodbye for now.